A question is, how many times do you have to shuffle a deck of cards to mix it up? I mean by shuffling, probably what you mean by shuffling. You cut them about in half, you go like that, and you push them together, right? And how many times do you have to do that till the cards get all mixed up? And there's a practical answer. The answer is about 7. And it's not, I think it, or it feels that way. It's a theorem. In contrast, there's another way that people shuffle cards. They shuffle cards this way. You've seen people shuffle cards that way.
That's how I shuffle cards.
Okay, well, and in India they do it this way. It's the same, you can see it's the same, dropping little clumps one after another. And so some people shuffle that way. And the answer to how many of those shuffles does it take to mix up cards is about 10,000. So it makes a difference.
Yes.
It makes a difference. There's a third way of shuffling cards that is used in tournament poker games and is used in Monte Carlo. I call that shmushing. So that's this method of shuffling cards. You've probably seen somebody do that. You might have done it yourself. And then you gather them up and hope for the best. If you shmush for a minute, it passes all the tests we've ever thrown at it. If you shmush for 30 seconds, it's sort of on the edge, but seems okay. And less than that, it starts failing tests and somebody could make money against you or guess cards right. Suppose you had a scheme for shuffling cards, one of these schemes, and you wanted to think about, is it working, is it random, or what am I talking about? If it was a few cards, suppose you had 4 cards, and you had some scheme for shuffling them, I don't know, some specific scheme, you could just try it a lot. With 4 cards, there are only 24 possibilities. The top card can be any of 4 cards. The next can be any of 3. That's 4 times 3 is 12, times 2 is 24, and then this is forced to go left. So you could just do it 1,000 times and see, do all 24 possibilities occur about equally likely? But with 52 cards, there are about 10 to the 68th arrangements of a deck of 52 cards. It's more than the number of particles in the universe. Okay, so one way of defining randomness is to say all arrangements should be about equally likely. I'll say a sort of more practical version of it. Suppose that you had a scheme for shuffling cards, and then we were playing a card game, and you had to guess at the cards one at a time as I turned them over. So for example, take a guess. What do you think the top card is?
6 of spades.
Maybe upside down, not so bad, Brady, not so bad. I think, 6, 9, it could be. Okay, but suppose, as in a card game or in a casino, the cards were turned up one at a time and somebody tried to guess what they were. Now, we know now that the 9 of spades is out of the deck, so you're not going to guess that again. What do you think the next one is?
Jack of diamonds.
Not so good. Okay, so no, but of course it's not so good. Your chance of being right on the first card is 1 in 52, if the cards were perfectly mixed. Your chance of being right on the next card is 1 in 51, then 1 in 50 if you have a good memory. And if you have a really good memory, if the cards are all turned face up, you would know what the last card is for sure. It's the matching 9. If the cards were perfectly shuffled, you expect to get 1 in 52 plus 1 in 51 plus 1 in 50, etc., right in going through the deck one at a time. And that adds up to about 4.5. So if somebody could remember and was guessing, but the cards were well mixed, you can get about 4.5 right on average. If you don't riffle shuffle enough, if you riffle shuffle 4 or 5 times, somebody can get 9 or 10 cards right on average. Anybody would say that's not random. Riffle shuffle is this guy. You riffle them together is the way we say it. They sometimes do it on the table this way. A casino dealer will do that. That's riffle. This is called overhand, and the other one I call shmushing. I wanted to say it's not just experimental that gives us these numbers I gave you, 7 shuffles. It's math, and I wanted to try to explain a theorem. And I think this is one that I can explain without writing anything down. Let's see if I make it. I'm going to take a very simple shuffle, which is take the top card off and put it in at random. You might put it back on top, you might put it back second from the top, you might put it on the bottom. It's intuitively obvious that if you did that a lot, the cards would get all mixed up. I mean, it's a silly way of shuffling, but it is like a riffle shuffle where you just happen to have cut off one card. I'm riffle shuffling this one card, into this big deck, putting it in at random. The deck starts out in order, you know, ace of spades, two of spades, three of spades, whatever. And there's some card at the bottom. I'm going to suppose it's the king of hearts. So the deck is in order. You know the order of the deck. It's in order.
That's how it came from the factory.
Yes, yes. Or you might have written them down. Guys in casinos, you know, record them as they come off. Right, how it came from the factory. And now you're taking the top card off and poking it in at random. And you just do that a lot. Okay, poke, poke, poke. Now, eventually, because of the rules, some card will go underneath that original bottom card. The king of hearts, there it is on the bottom. Eventually, if you wait long enough, a card goes underneath the bottom card. How long does that take? Well, the chance of a card going underneath the bottom card is 1 in 52, because there are 52 places it can go. And so the chance of the event happening is 1 in 52. Therefore, it takes about 52 pokes on the average to have that happen. Okay, and now keep going like an idiot, and eventually a second card goes underneath the king of hearts. When I put that second card underneath the king of hearts, so there are two cards there, even if I told you, hey, it's on poke 503, I just poked the second card underneath the king of hearts, it's equally likely that the two cards underneath the king of hearts are in order low-high or high-low. Because I'm poking the card in at random. I could have put it above the card that's on the bottom or below it. I'm poking them in at random. Now, keep poking. Eventually, a third card goes underneath the king of hearts. There are two cards previously. This one, there are two cards. This one goes in here, here, or here at random. So all 6 orders are equally likely. Every time you put a card in, given as long as you're putting it in at random, the cards underneath the king of hearts are in a completely random order. I hope that's intuitive, and it's true.
It makes sense.
It makes sense. And now look at what happens. You keep poking. The king of hearts event slowly moves up. It never goes down. It might stay where it is. If I put a card above it, it stays where it is. But if I put a card below it, it moves up by 1. So eventually the king of hearts comes to the top. By induction, by the argument we've been doing, all the 51 cards are in a random order. When I put the king of hearts in at random, the whole deck is random, exactly random at that moment. Every arrangement is equally likely. So that is not only intuitive, it's an exact mathematical fact, but I hope it makes sense. I think it makes sense. And now you can just ask, how long does that take? Well, it takes 52 pokes for the first card to go under. There's the king of hearts on the bottom, then I put a card underneath it. So now there are 2 places the next card could go. So it's 2 out of 52. So it takes 52 over 2 pokes. And then it takes 52 over 3 pokes for the third card to go under. So it's 52 plus 52 over 2 plus 52 over 3. And that answer is, well, what is it? It's 52 times log of 52, which is around 200 or so. So it takes about 200 of these pokes. If you shuffle fewer times, if you shuffle 5 or 6 times, it really somebody can really make money against you in a card guessing experiment. If you shuffle 10 or 11 times, it's not worth the wear and tear on your shoe leather standing there in the casino if you're counting cards. It's just as close to random as it could be. Of course, it's never perfectly random. You have to shuffle infinitely often to make it. There's still some trace of the original order, but it vanishes exponentially fast. So, wonderful question. Let me try to match you with an answer. The model that the 7 shuffle is based on, I'm going to say it as a slightly more mathy thing.